Hello, in this video, I want to talk about using logarithms when collecting data. So you may wonder why especially in chemistry, we have some formulas that seem very complicated and use logarithms. So I just want to very quickly go over why that is the case. So it's pretty common to have graphs of data. And our favorite kind of data to collect, because it's the easiest to analyze, is data that looks something like that, where you have some y dependent upon some x, and the data comes out very nicely like those dots, okay? The reason we like that is if I were to try to put a line through there, all right, it's very easy to either by hand or using some data processing to get a best fit line. And hopefully you remember that this best fit line has some equation y equals mx plus b. It's pretty easy by looking at the data. Once you sketch in the line, you can just look at a total delta x and delta y, and m would be the slope, the delta y over the delta x, and then over here we have our y-intercept, and we could get a b value, and then we have a model for our data, right? But usually data doesn't fall in a straight line like that, or often it does not. Okay, we wish it did, because then the math of analyzing it is easy. Often the data will look something more like this. So let me sketch a quick set of axes here. All right, and pull out my yellow pencil here. And often the data ends up doing, something more like that, okay? And when we look at that, it's clear we have data that's not linear, okay? If we tried to put a line into that data, down here, we'd have a line that looks something like that, which doesn't at all represent what's happening later on. And up here, we'd have a line like that that doesn't at all represent what was happening down at those lower values. So what happens, let's erase that line. So if this is y and this is x, we need a different kind of relationship to describe it, okay? In this case, probably a good curve is something like this. That's not a bad curve, all right? Probably could do better to get a best fit curve, but that one's not bad, all right? And this curve is more of an exponential kind of curve, all right? So you've hopefully learned about these, but this is in the form y equals a e to the kx, all right? Now let's talk about what a and k would be in this context. E is the exponential base. Sometimes this all works just as nicely, and in science, especially in previous eras when you didn't have computers doing this for us, it would often be 10k to the x, because 10 is easier to work with using different kinds of graph paper and whatnot. But in today's age, we usually use the natural base. But what is a? Well, a is what you would get when x is 0, all right? If x is 0, you would be right on, it would be the y-intercept, right? The y-intercept value is your a. So that would be easy enough. If you graphed a best fit line, it would be pretty easy to figure out about what a should be. And for exponential growth, that's sort of your starting amount, your initial amount of whatever is growing. All right. And then K would be the growth rate. Okay. So that's the number that determines how quickly you would grow. Okay. Now, the problem is, from this graph, there's no way to figure out what that growth rate would be. You could, make guesses until it fits reasonably well, but we want a better method than just guessing. Okay, so here's where logarithms come in. If y is equal to a e to the kx, I'm going to work with natural logs, but you could use the log of any base. We can say that the natural log of y, is the natural log of a times e to the kx. Then there are a series of rules of logarithms, which I'll write out to the side. So the first rule of logarithm that we're going to apply is that the log of a times b is the same as the log of a plus b. Log of a plus the log of b. Okay, so what we can do is we can take this relationship we have here, ln of y would be ln of a plus ln of e to the kx. Well, hopefully you remember with logarithms, if you have that logs are what undoes an exponential function. So you have the log base e of e to the anything, e to a power. Those will undo each other and we're just left with the power. Okay, so that means we can rewrite this relationship as the log of y is equal to the log of a plus kx. Right, now why is that useful? Well, it turns out we've just linearized the data. Okay, so if we were to graph ln of y, whoops, let me rewrite that, ln of y versus x, then when we look at this data, okay, this ln of y is what gets plotted instead of y, so that's what would go in over there. Ln of a is a constant like b, okay, when we're dealing with straight lines. K is a constant like m, and x is the variable x. So we have ln of y is equal to b plus mx. Well, that's a linear relationship. So if instead of plotting the data y versus x, we turned around and took that exponential growth and we were to plot, let me just sneak this in here. I sneak my pencil too. Here, and we plotted the data as ln of y versus x instead, we would end up seeing that we get data that looks more like that again, where this is ln of y and this is x. So we can fit a straight line to it. Okay, once again, you can statistically do this. That's usually what you would do if you had some kind of Excel program or just in your graphing calculator, or in the old days, you might have sketched that by hand and then determined its slope and its y-intercept. Okay, so here would be the y-intercept, b, and we just mathematically showed that b would be the natural log of a. Therefore, a, once you determine what the y-intercept is, you could find the initial amount is e to the b. Okay, and you could compare that to the initial amount we have on the original graph. They should match up if you've done this well. But more importantly, we can determine the slope of this line pretty easily, and the slope is the k value. So that's the growth rate. So we just determined the growth rate by linearizing the data. So it would be a wild guess looking at the original data to figure out the growth rate. Once we've linearized it, it's not a wild guess, right? Now let's use logarithms for one more type of relationship, right? So let me put in another set of axes here. All right, and let's say that we have data that looks like skew it just a little bit more. Okay, so the data is something like that. Okay, so clearly we have some sort of concave relationship here. So there's y and there's x, but this time it's not growing from some value. All right, let me put in the green line. It's starting down here at the origin, and we seem to have a curve that looks more like this. All right, well, maybe that's y equals x squared. It's likely that it's y is equal to some constant, we'll just call that a again, times x. It could be x squared, but maybe it's x cubed. Maybe we don't know. Okay, it's x to some p. all right? And once again, trying to find P is just a matter of guesswork if we're just looking at that graph. So what can we do if we have a data that looks like that in order to be able to figure out what it's doing? Once again, we can use logarithms. So let me just start with the equation y equals ax to the p. If we take the log of both sides, we can repeat the rule of logarithms that we used before and say this is ln a plus ln of x to the p. All right, where x is our variable. Okay, now if we look at this, there's another rule of logarithms that we need to pull out, which is that, I'll write it beside here. If you have ln of x to the p, it's the same as p times ln of x. So let me rewrite this one more time. The ln of y is equal to the ln of a plus p times the ln of x, okay? Or the log of any base, doesn't have to be natural logs. All right, well, why is this useful? Well, if we group this, if we were to plot the natural log of the y values versus the natural log of the x values, we've just linearized our data again. All right, so let's see why. Okay, so if we compare this to y equals ln of a is a number, because a is a number, so the log of a is a number, so that would just be our y-intercept again. Okay, and then plus, well, p is like the slope of a linear function, and we use ln of x instead of x. We just linearize this again, where if we look at this, the slope of the line we get will be our power, all right? And the y-intercept can show us what the a value should be in that relationship. Okay, so if we were to graph this original data as logarithmically, let me just put in a side-by-side graph here. So if I do this logarithmically and we plot the data, all right, it should end up being something more like this now, where this is ln of y and this is ln of x, and we would get a nice line through the data. All right, and it would be very easy to pick off a b value, and it would be very easy to pick off an m value for a straight line, and m would give us the p of the original relationship. So coming over here, we're trying to figure out what a is and what p is. So the slope of our linearized data would give me the p value, and b could end up giving me, let's switch back, that would be equal to the log of a. So a would be e to the b. So by pulling the y-intercept and the slope off of the linearized data, we can figure out the constants to put in our power function. So once again, this is a power function. So if the original data is more like a power function, you'll want to do a log relationship of the data in order to linearize it. And going back to where we were before, if the data is more exponential, then to linearize it, you just take the log of y, and that will linearize the data. And it works equally well for exponential decay. You would just get an m value that's negative. So whether you have exponential growth or decay, using a log of the outputs will linearize it. If it's a power function though, and that power could be a root, it could be a square root as well as a number bigger than one. If you have a power relationship, you can linearize it by doing a log versus log of the data.